Awesome. Thanks everyone for making it today. Got lots of people that are joining here. It looks like we've got an entire team. It looks like from Solvest from in the Yukon territory. So thanks everyone for making it. Um, we've got Harsha Kumar from Fronius Canada. Harsha, what's your title there?
Oh, I'm the manager for technical support here.
Perfect. So we'll be talking a little bit about best practices when installing Fronius inverters and all of that good stuff. And Fronius and us, we've been working together. I think like it's been like since 1991. Going back to our parent company back in the day in Germany. And then Fronius being an Austrian company, it's been a really long time, and I think Fronius was the second manufacturer at Frankensolar that was set up here. So going like way back to the beginning in Canada with us to 2011. So it's always been a really good relationship, and they have really good products and a really good value proposition. So we're very happy about the relationship. With that being said, Harsha, really appreciate your time. If you want to go ahead and start your presentation.
Sure. Well, thank you for having me. And without much further delay, let's get started. My name's Harsha Kumar, and I work as a manager for technical support here at Fronius Canada. And we work out of our offices here in Mississauga and support all of our customers across Canada and sometimes overseas as well. I have a background in power systems and electrical engineering and renewable energy, and a lot of that, brings a lot of value to me in my position here. So Fronius was started by Gunther Fronius in his garage in 1946, and when at the outset, they basically started off by making chargers for automotive batteries, and Fronius's strength is basically in power conversion from DC to AC and vice versa. And you can see that all three of our business units leverage that expertise. So perfect charging is for battery chargers. It started out for automotive chargers, but now they charge batteries across the board. Then the next business unit to come through was the perfect welding, which again is power conversion. So again, it was the same power electronics technology. And then the youngest of our business units is solar energy. And the parent company started the solar energy business arm in '92, but we've been in the US market since 2002 and in the Canadian market since 2011. So we did start off with our own assembly line as well here in 2011, because at that time, we were here to meet the market needs for the FIT program in Ontario. And one of the requirements for the FIT program was to have manufacturing in or on Canadian soil. Now, that assembly line doesn't exist anymore because it didn't justify the expense anymore. And also that requirement doesn't exist anymore, that you need to have your inverters manufactured in Canada. Now, in terms of our product overview, currently, we do have inverters that are used at both 600 volts DC and 1000 volts DC. Now, the example I have for you here today is the Fronius SIMO. The SIMO is, a three-phase inverter. So the three-phase inverters on the AC side come in 2 voltages. It can be 208 volt delta, in which case you do not need a neutral, or you can also have it at a 480 volt Y, in which case you do need a neutral. Do bear in mind that the neutral conductor is what we call a sensing neutral. So there is really, the conductor need not be fully rated because you do not have full device current on the neutral. So the neutral here again is what we call a sensing neutral, but also the auxiliary functions on the inside of the inverter itself. They do draw a little bit of power. So if you do need specs on sizing the neutral conductor for each inverter, size it for about 1 ampere consumption. So depending on your cable run, you might have to size that accordingly. Now, I did tell you that these inverters can work both at 1000 volts DC and 600 volts DC on the DC side or the array side of the business. Now, not all inverters work on both voltages, so you have to keep that in mind. The primos on the DC side are actually designed for 1000, but will work just as fine even at 600 volts. So the primos can work both at 600 DC and 1000 DC. The SIMOs 480 volt inverters on the DC side are exclusively 1000 volt inverters. So you should not be stringing up the array for 600. If you do, you will have suboptimal production on those inverters. The SIMO 208s come in two types. You can have the SIMO 15208, okay? That is a little different compared to the other SIMOs because that particular SIMO was built to be used as a ground-mounted inverter for a ground-mounted array. And so it only has one MPPT, and also it does not have a bleed down circuit, so which makes it incompatible with rapid shutdown requirements, because rapid shutdown has two components to it. One is disconnection and the second is bleed down. The disconnection is done by whatever device you have mounted close to the array. The bleed down itself is actually an internal function of the inverter, which is done by the filter circuit. And that particular model of inverter does not have that bleed down circuit built into it. So it is incapable of rapid shutdown. But on the 208 inverters, you can also have the SIMO 10208 and the SIMO 12208. Those are both 600 volt inverters on the DC side. The SIMO 15208 is a 1000 volt inverter on the DC side. So please keep that in mind. Another thing you want to keep in mind is whenever you design the array or the strings that you do want to connect to a particular inverter, you need to be aware what the limitations are for the rest of the, what should I say, the components, which we call the BOS components, that is balance of system components, because the balance of system component, the component with the lowest voltage rating is the design constraint for everything there. It's kind of like the weakest link in the chain approach. So the weakest link in the chain decides how strong that chain is. So similarly, on the DC side of the business, whichever component has the lowest voltage rating, he decides the voltage rating for your system, and that inherently is the voltage rating for your system. So on the DC side, if you are going to be stringing up something for 1000 volts, but maybe you purchase PV modules which are only rated for 600, then you cannot go beyond 600, because if you do, then you're basically abusing the device, the component that is rated for 600. Okay, now we was just speaking about the different versions that you have here. So I'm mostly addressing the SIMOs throughout the presentation, but what we do address is also just as equally applicable for the primos as well, which are the single phase inverters. Now the 208 versions, I believe we have likely the largest inverter on the market, which is a 15 kilowatt, but you can, which is a 1000 volt inverter on the DC side. And given that it's a 208 three-phase delta connection, you do not need a neutral for the 208 inverters. Okay, so this is just a bit about the cut sheets for that. Now, one thing that you have to keep in mind whenever you design strings for working with inverters, irrespective of who the manufacturer is, you always want to keep in mind that you design the strings for the highest operable voltage well within the inverter's safe limits. For example, when you do design your strings, most people often tend to use other simulation softwares. You could use Helioscope, etc., or some other third-party software. Always, when you do run your simulations or designs through those sorts of software, please make sure that you also run your whatever design you zeroed in on through the inverter manufacturer's tool as well, because those softwares are only looking at it from a production perspective, but it does not take into account the device constraints. So the device constraints are something that are which are usually built into the inverter manufacturer's design tool. So if you do need to run it through your Helioscope, simulation, run it through there, and then run those numbers through the Fronius string design tool as well. I'll take you to that in a bit. So that way, that from a production perspective, you're getting a good string design, and from the device safety perspective, you're also not going to destroy the device at the same time. Okay. Having kept that in mind, also make sure that you are well aware of what the extreme temperature constraints are on the site. Okay. So for example, on the low side, you always want to find out what is the lowest expected site temperature. And so you can have that as your, the minimum temperature when you do design your strings. On the high side, typically always tend to use 75C, okay, simply because even though your air temperature might not cross 30 or 40 C, your PV modules themselves can easily be running much, much hotter. And the higher the operating temperature, the lower is the string voltage. And so if you choose to go with short strings, it is very likely possible that in the peak of summer, you might have just dropped the string voltage outside of the inverter's MPP voltage range. So always when you are making string designs, make sure that you meet the operating voltage considerations on both sides, the low side and on the high side. When I say low and high, I'm referring to the temperature, because the lower your site temperature, the higher the open circuit voltage. Okay, so if you end up designing it for -20, but the site went to -40, then at -40, you might be reading something like 1100 volts DC coming into the inverter, and you would have basically popped the inverter already. That's on the low side. Now, on the high side, if it got too hot, so maybe you had a heat wave and your air temperature was 40 C, but your PV module temperature could itself easily be about 80 C. And so at 80 C, you want to make sure that the string voltage is still within the inverter's MPP operating voltage. Because if it isn't, then you will have suboptimal production. And do keep in mind that MPP operating voltage and inverter operating voltage need not be the same. What I mean by that is, the inverter might wake up in the morning, because your string voltage was 300 volts, okay? But in the afternoon, if the temperature was high enough, then your string voltage coming in from the array side could be 200 volts. And so the inverter is awake and alive and producing, but you're not exactly in the, what should I say, sweet spot when it comes to the MPP operating voltage. Okay, so this again is a bit more information about the cut sheets and all that stuff. Now, one thing you also want to keep in mind is when you design your strings and how you bring them into the inverter, all of this has to be taken into consideration with two things in mind. One is safety perspective, and the second is the efficiency perspective. So for the safety perspective, you want to make sure that you're not going to blow the device, and you can blow the device through voltage, as in too much voltage, or through too much current. And when it comes to current, there's two sides to it. So a lot of people, what they do is they only look at the inverter's operating current, but not at the, not the inverter, sorry, the array operating current, and not at the array short circuit current. So array operating current is, when it's under regular operation or, normal operating conditions. Short circuit is something that you have to design for, because all PV modules, or basically, any PV array, is what we call, what should I say? It's kind of like if you were to create a short circuit on the utility side of the business, the normal operating current and the short circuit current, the ratio between them could easily be several thousands. But on PV modules, your normal operating current and your short circuit current aren't really all that different. So your normal operating current could be about 80% of what your short circuit current is. So which means that even if you did have a short circuit going on, really, because the difference is so small between the normal operating current and the short circuit current, you might not even notice that you've actually had a short circuit. Okay. Now, is that safe? Is it not safe? It depends on how many strings you've got and how many such strings you've got in parallel. All right. So the first rule of thumb is whenever you're designing an array to be connected to an inverter, we talk about string fusing. String fusing, you need to keep in mind, is actually not for the protection of the inverter. The string fusing does not protect anything on the inverter. The string fusing is protecting the PV modules, the PV array, and the PV cabling between the array and the inverter. All right. So now, if you did go back to your cut sheets and all that stuff, you will see that there is something called short circuit current that is listed at NTC or STC, which is standard temperature and pressure conditions, which is usually 25 C. So, which meant that if the air temperature was that, and for whatever solar radiation you are receiving, if you were to create a short circuit, that PV module is capable of making that much short circuit current and supplying that much short circuit current. But you also have to understand that if it is capable of making or supplying you that much short circuit current, it means that the PV module and the cabling that come with the PV module, they are also rated to handle that much short circuit current. So if they are rated to handle that much short circuit current, it means there really is no risk if you were to create a short circuit with that much short circuit current on it. Now imagine I strung up a series of PV modules to give me, what should I say, the string. And now usually you don't build a PV array with just one string. You will have several such identical strings in parallel. Now supposing I have two strings in parallel, and I've got a dead PV module on one of them, creating a short circuit. So you'll see that the good string, because it has more PV modules or working PV modules on it compared to the other string on which you probably have one or more failed PV modules. So there is a voltage mismatch, which means now that the good string is going to dump all of its current, short circuit current in this case, on the bad string. But given that they're both identical PV modules on both these strings here, and it's a series connection, you will have one PV module or one string's worth of short circuit current from the good string being dumped on the bad string. But we already know from the PV module manufacturer's cut sheet that the bad string is capable of handling one string's worth of short circuit current, because if I'm making you that much short circuit current, I'm also going to be safely able to handle that much short circuit current. So when I've got only two strings in parallel connected to the same MPP tracker, fusing is redundant. But if I exceed 2 strings in parallel connected to the same MPP tracker, then you need to start fusing, simply because let's assume now I've got 3 strings in parallel connected to the same MPP tracker, and I've got a dead PV module on one of the strings. Then now I'll have 2 strings worth of short circuit current that's being dumped on the bad string, but the bad string is only rated to safely handle 1 string's worth of short circuit current. So that is why you now need to start fusing. Okay, so when you fuse there, again, although the fusing is to protect the PV module, PV cabling, PV array, remember that all of these are in series all the way into the inverter. And on the inverter's terminal block is where the paralleling actually happens, unless, of course, you have a combiner box preceding this connection. In which case, when you fuse, you have to make sure that fusing is always used only when you go over 2 strings in parallel on the same MPPT. Okay, that's one thing. The second thing you have to keep in mind is the fuse rating in terms of how much current and voltage it is rated for should be specific to that particular PV module short circuit current. Because you have to remember that like I said, on the AC side, if you have a 35 ampere breaker or a 50 ampere breaker, all right, when I create a short circuit, the utility is considered an infinite source. So the amount of short circuit current that comes through that breaker to the short circuit point could be 5,000 amperes. And the way the AC protection system works is the higher that short circuit current in relation to the normal operating current, the faster the breaker trips. So it's called an IDMT curve. And so it's inverse definite minimum time, which means that if I've got a 35 amp or a 50 amp breaker and my short circuit current is 51 amperes, that breaker literally will never trip, because it's based off of heating a bimetallic strip on the inside. But supposing on a 50 amp breaker, I created a short circuit and now the short circuit is 5,000 amperes, it's pretty much instantaneously going to trip because the ratio of short circuit current to the normal operating current is that high. Now, use that logic on the DC side of the business. So the same logic works even for fuses, not just for circuit breakers. So your fuse, again, if I've got like a 200 amp fuse on a 200 amp bus bar on a 200 amp service coming in, when I create a short circuit on it, I could get 2,000 amperes passing through that fuse, which means that fuse will pop almost instantaneously. But for a solar PV module, if it's a 10 amp normal operating current and 11 amperes short circuit current, when I create a short circuit on that string, there isn't any much difference between normal operating current and short circuit current. So if I did not design my fuse capacity properly, that fuse is never going to blow, even though I've got fusing there. So merely having the fuse there isn't going to serve its purpose. You also have to make sure that you pay attention to the design of the fuse when it comes to the fuse's interrupting capacity and what it's normally rated to handle. Okay, so keep that in mind. And the last thing you want to keep in mind is also, if you do use a combiner box before you have to get the array or the cabling into the inverter, keep in mind that on the back of the inverter, you have screw terminals, and each of those screw terminals is rated to handle you 1 string's worth of short circuit current, which is 15 amperes typically. Okay, so if I use a combiner box now, I'll have a single cable that's coming into the inverter, and that single cable likely will contain more than 1 string's worth of current on it because of the combiner box. So it could be 2 strings, it could be 6 strings. But since you're getting it as 1 single cable into the inverter, make sure that you do not land it on a single screw terminal, because if you do, you're literally overpowering that screw terminal and you might fry that terminal. So which is why we also supply. Yeah, go ahead.
I have a quick question. Do a lot of people use combiner boxes with your inverters?
Yes, it depends on the place. For example, in Manitoba,
let's exclude Manitoba because Manitoba has a different rule there. But outside of Manitoba, is anyone using combiner boxes?
It depends on the installation. I'll also get to that a little bit further. It's actually beneficial to use a combiner box. I'll explain why. Okay, yeah, so combiner boxes are used extensively, not just in Manitoba, outside as well. It also depends on the engineer who designed the system and what they were looking for. And it is very valuable to have a combiner box. I'll explain that a little bit further once we get into it as well. Right? So again, so safety perspective is not just voltage. And when we talk about voltage, usually the higher the voltage, the worse it is, in the sense that you'll pop the inverter. That didn't mean you should go low, because if you go too low, you might fall outside of the inverter's operating MPP range. Okay, that's for the voltage. And when it comes to the current, again, so always make sure that you design everything for the rated voltage, the safe operating voltage, and make sure also that you design it for your short circuit current. Okay, one additional thing you want to keep in mind is by code, a lot of people design the 1.25 or a 25% over when it comes to voltage and current. But keep in mind that that is something that we exclusively follow only in North America. So nobody else outside in the rest of the world follows that rule. So sometimes you might be in a situation where It might be safe for the device because that's how it works, but you might be in violation of code. So you have to make sure that you are not in violation of code when you make these designs. Okay, I'm just going to, sorry. Yeah, so now coming to the second part of it, which is basically, now you got all of your string designs, etc., all of that stuff, and yada, 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 and you think it's safe because you ran it through the string design tool as well from the inverter manufacturer. Now you have to keep in mind that your array is, so what should I say, is one unit, but depending on what kind of inverter you are connecting that array to, that inverter might or might not have 2 MPPTs. Now, across the board, Fronius inverters have 2 MPPTs, but for one exception, which is a SIMO 15208, which only has 1 MPPT. Okay, so the inverter construction, the wiring, the mounting bracket, the terminal block, everything looks identical, but on the inside of the inverter, that particular model of inverter has only one single MPPT. So keep that in mind. If you do need to use that particular model of inverter on arrays where you might have more than one string length or more than one orientation or more than one azimuth. All right. So keeping this in mind, what is the benefit of having more than one MPPT? So MPPT is short for maximum power point tracker. Right. So if you worked with solar for long enough, you know how the cut sheet for a PV module looks like and what the plot for the IV curve of a PV module looks like. So anytime you work with a PV module or with a PV array, the job of the inverter is to get as much out of that array as possible, which kind of corresponds to the sweet spot on the IV curve, which is the knee of the curve. Okay, and keep in mind that that curve that you see on the cut sheet, it looks static, but it actually isn't static because that curve is a function of temperature and radiation, okay, and also soiling on the PV module, which means because the temperature is changing all the time, and so is the radiation, and the soiling is not under your control, there is no way for you to predict what is, or rather how much or where you are on that curve. Okay, so the thing that should always be at the back of your mind is that curve is not static; it's always moving. So the job of the inverter is to play catch by making sure that you are operating the inverter such that you are at the knee of the curve, which is a sweet spot. Right, and given that we are quite a ways away from the equator, the duration of day length and also the angle at which the sun hits the array is also moving, and is there's a big difference between the radiation and the duration of length in peak summer or in peak winter. So keep that in mind as well. So why is all of this relevant is because on the inverter, you have the MPP tracker. MPP tracker is basically the inverter's inbuilt circuitry to be on the sweet spot of the array. And given that the sweet spot is moving all the time, you're always trying to play catch with it. And so the inverter, what it does is there's an algorithm on the inside. What it does is it sweeps the curve. And depending on how you've got shading or soiling, etc., or you might have clouds moving across the sky, and so which basically means that you have shadows of that cloud moving across the PV module. So the inverter keeps sweeping the curve at a certain fixed frequency. When I say frequency, you could sweep the curve of the array at 1 minute intervals, 2 minute intervals, 5 minute intervals. Now all of that is specific to each manufacturer, and these are usually proprietary information. So what the inverter does is he sweeps the curve. Okay, and he settles on the sweet spot because that's the place where he's currently getting the most amount of power, or you've already hit the amount of power that the inverter can safely get out of it. So there's two sides to it. One is like supposing you have a 10 kilowatt array, okay, and you do not have that much radiation falling on it, then the inverter will try to get the most out of it. But you might have a 10 kilowatt array connected to a 5 kilowatt inverter, and if it's peak summer, you can't get more than 5 kilowatts out of a 5 kilowatt inverter because that's the inverter's rated capacity. But if I've connected a 10 kilowatt array to that inverter, it means that there is more than adequate power available from that array, but the inverter is limiting itself. So there's no point in sweeping the curve in that case. So what I'm trying to get there is the opposite is going to happen to you in winter or during periods of low radiation, because now you might have a 10 kilowatt array, but because you do not have enough radiation, the inverter might only be able to extract about 3 kilowatts out of it. So then you might come back and ask us, what's the point of having a 10 kilowatt array connected to it? That because you're overpowering the inverter. The reason to overpower the inverter is because you want to be, what should I say? Your design intent is to make sure that even in the leanest of seasons, you're still able to get as much power out of the array as possible while still being within the inverter's safe operating limits. Now, I did speak to you earlier about the safe operating limit when it comes to current and voltage. There is a third parameter that is also called the inverter ratio. Inverter ratio is basically the size of the array over the size of the inverter's AC capacity in watts or kilowatts. So for most inverters, for most Fronius inverters, the safe operating limit is 1.5, which means I can connect 1.5 times the AC kilowatt capacity of the inverter through the DC side. So if I've got a 10 kilowatt inverter, I can connect 15 kilowatts worth of DC to that 10 kilowatt inverter. So the ratio is 1.5 or 150%. Now that is true for all Fronius inverters across the board, but for one exception, which is the SIMO 15208. And that the oversizing ratio, the inverter ratio for that one is 1.3 or 130%, which means you can only go 1.3 times 15 kilowatts for the 15 kilowatt 208 inverter. So that's the third safety limit, right? Now coming back to the MPPT, now I did tell you already that the curve, or rather the the moving curve, is because of the changing radiation, etc., all of that stuff. Now assume that you are on an east-west roof, and I've got a portion of the array on the east side and a portion of the array on the west side. Now, given that they face different directions, the time of the day that each of those portions of the arrays will hit their maximum peak production is going to happen at different times of the day, because the sun isn't hitting them both at the same angle, at the same time. So for example, take this particular one in the first picture on which you've got an east-west facing array, right? So the east side, the portion of the array facing east is going to get lit by the sun till noon, and post noon you'll have the sun hit the west side of the array. Now, if I were to put them both in parallel, the side that is lit is going to work like a fully charged battery, and the side that isn't lit is going to work like a weakly charged or a discharged battery. And when I put two such batteries in parallel, the good battery is going to waste all of its power on the bad battery rather than sending the power into the device that is supposed to power, simply because there is a voltage mismatch between them. And since power always flows from a string or a source with higher voltage to a place with lower voltage, the lower voltage here was going to be the array that isn't lit at that time. So if I put them in parallel, I'm kind of shortchanging myself because you're compromising the production from the system. So this is where having more than one MPP tracker comes into use. So you can put the side that is facing different directions or different orientations or different azimuths on different MPP trackers. So if you do that, that way each tracker can function as if it was an independent inverter without compromising the production on the other array. Okay, so you might in theory have like a 20 kilowatt array, okay, just as an example, and I got 10 on the east and 10 on the west. But if I did not set them up as two separate MPP trackers and I put them in parallel, you quite likely are working it as if it was a 5 or a 10 kilowatt array as opposed to 20. So always make sure that that this is something that you have to keep in mind during the design stage itself, because remedying such things are usually it's going to involve a lot of effort and restringing after, if you try doing this after. Right? And also do keep in mind that the MPP trackers, in terms of capacity, they are not symmetrical. So MPP tracker 1 is not exactly 50% of the converter capacity. It's about 2/3 capacity is allocated to MPP tracker 1 and 1/3 is allocated to MPP tracker 2. So all of this is relevant and useful for roofs which are not what should I say, uniform, or if you have shading or other things like shading could be again due to adjacent buildings or smokestacks, etc., or you could have like vegetation around you. So there's different ways to address such installations, and all of this has to be kept in mind when you are making the string design. Now, this might look like a lot of overkill, but you have to keep in mind that when you build any such system, renewable energy system, you're usually looking at it over in the long term, in the sense it's 10, 15, 20 years. So keeping all of this in mind will save you a lot of headache and trouble in terms of trying to fix production issues, etc. later on. So doing due diligence or your homework before you actually get to start physically assembling and putting things together pays off big time. So again, if you have two different directions or two different orientations or two different azimuths, always choose to go with a multiple MPPT inverter. And just going with a multiple MPPT inverter isn't call, the crew on the site needs to be informed and made well aware that when you string it up, you've got to string up the array also such that, I mean, in the sense, you can have an east and west facing array. But if they've taken like, a few modules from the east and a few modules from the west and made it one string and put it on two separate MPP trackers again, it's kind of, you're working at cross purposes there. So always make sure that everybody in the crew is well aware what's going on and how the logic works, because if they don't, they might string it up thinking they're doing it right. So on paper, your cut sheet, your SLE, etc., might tell you this is how it should be done, but there's no guarantee that that's how it was actually implemented on site. So always make sure that the crew understands what you're doing and what the intent behind that particular design is. So that way they will be, less prone to error.
Yeah, and even if you have any questions, I mean, feel free to reach out to your Frankensolar key account manager. We're happy to help out with string sizing and all of those questions. It's really not rocket science. It's, once you kind of understand the principle of it, it's really quite straightforward. But yeah, we're happy to look over any designs here. Feel free to reach out if you're not 100% sure how it works. Yeah, anytime.
Yeah. So always, so I mean, if you have doubts or questions, or if you're not sure, ask, all right? Because it's like a lot of people are hesitant to ask because they think, you might sound dumb, but believe me, asking is better than finding out later that something went wrong. Or
yeah, I think the big, like what we see, some people when they switch over from a microinverter to a string inverter, for example, the biggest issue we see sometimes is that the string length is too long. I think that is probably the biggest worry, specifically in some other manufacturers that are. I think the one advantage Fronius inverters have, or one of the advantages, is that even your small primos will work at 1,000 volt technically. But even though it's not not legal to string an inverter over 600 volt in a dwelling, if for whatever reason someone were to add an extra 2 panels, nothing bad is gonna happen.
Exactly.
However, if you're doing the same thing with a 1,000 volt inverter and a 1,000 volt application, or with another inverter that is only rated for 600 volt DC, and now you're adding 2 panels, and now it's minus 40 degrees Celsius outside, now your inverter may fail, and you may have catastrophic failure, and you need to replace that inverter. So whenever you're doing string sizing, just make sure that, and again, feel free to reach out to us. It's very straightforward. And after you've done it twice, I think you'll get the concept pretty quickly.
Yeah.
Just double check at the beginning to make sure you calculated your weather coefficient properly.
So again, once you understand the logic or the intent behind your string design and how you approach it, it'll make so much sense. Go ahead. Go ahead.
Yeah, just like, can you hear me?
Yeah.
Just with the 2/3 of the power on one MPPT and one, does that mean that if you had a fully loaded inverter, it was split some power on that second MPPT?
I think it's the amperage that is the difference, the amount of strings you can connect. It's not the power output. Once it goes past your MPPT, it just means that I think you can do maybe 3 strings on input 1 and only 2 strings on input 2 or something like that. Harsha can probably knows the exact amount of strings that you can do. But it's just the number of strings you can connect with onto that MPPT is different, not the actual power output.
Yeah.
Exactly. Yeah. Okay, so I'm going to talk to you now, or rather walk you through the Fronius Solar Creator. So this is the design tool. So always remember, you can run, or rather you would have, if you have run your simulations on your string design through another simulation software, please make sure that you still run it through this. So this is what I call a sanity check, in the sense that you're basically making sure that you're not going to blow the inverter because you might be exceeding the voltage, etc. So this is our page for this Solar Creator, and a lot of people actually miss this. So you got this little button there which says Go to Solar Creator. Were you to click on it, it'll bring you to this page. Now, if you on this page, the link I got the link here. I'll share the slides with you guys later. So once you come in there, the Solar Creator tool actually is made for, it's a common tool for both regular systems like what we do here, which are not, what should I say, storage compatible. But you can also design, what should I say, strings for inverters which are hybrids. Unfortunately, we don't yet have the hybrids in the Canadian market here, but the tool does include that, so you can kind of get lost. So to avoid that, what we did was there's a little button on it. It's called the Quick PV Design. You have to click on the Quick PV Design, and this is what you'll get to see if you do. All right. So this is what the tool looks like, and what I'm going to do now is walk you through the actual tool live. So here we are. We go to the Solar Creator. Now, if you have worked with Fronius systems in the past, especially the monitoring site, you know what SolarWeb is. So if you have a SolarWeb login, it's the same login here. You don't need to create a new one. If you don't have an account or you choose not to create one, you can continue as a guest. So I'm going to continue as a guest now. So this is the login page. Do you see the login page here?
Yes. Yeah.
Okay, so I'm continuing as a guest. And now do you see the page here?
Yeah, it's just empty though.
Yeah, perfect.
Yeah.
Okay, so because I'm a guest now, if I were to log into my account, you would see previous projects that were designed here as a list. Since I'm not signed into my account now, but I'm as a guest, you don't see anything here. So here I'm going to click on the Quick PV Design. So we are here at the tool now. So let's say that I intend to use Canadian solar PV modules. So I'm going to clear that off and start typing. And it'll filter the list down. So I've got Canadian Solar here. Then it's a database. So if the PV module is in the database, you'll see it here. If not, you can actually choose to add it in. You see, you got the little plus sign. So if it's a very old PV module, or you're retrofitting something and that PV module probably doesn't exist on the market anymore, but if you do have access to the cut sheet for that PV module, you can click on this and add it in here. All right. So do make sure that you have a cut sheet, because if you don't have the cut sheet, then you're putting in numbers which might not be real.
Okay.
Okay. So now let's say I'm going to choose this particular PV module here. And where it says the number of PV modules, do not change anything there. Please fix the site temperature.
Sorry, can you take a module that is relevant, like a, I don't know, like a.
No, I mean, I'm open. If you have a suggestion.
Yeah, just use like any
Longy.
like a
Longy,
Longy
please.
550 watt or something like that. Something people are actually going to use, right? With their system.
Okay.
They have like a 550 or something.
Sure.
545 HPD there. That was, but this works as well. Yeah, that works.
Okay.
Yeah.
Okay, so I'm going to leave the number of PV modules blank. And let's say we're designing for Edmonton. So I'm going to set this to -40. Okay, now depending on whether this is a bifacial or not, you can plug in your number for expected gain from the rear. Now do keep in mind that if you are expecting any gain from that, this is going to limit the size of the array, because this will add to the power production.
Harsha, could you make it a little bit bigger, possibly? Is there a way to just on people's screens? I won't. Yeah, it'll show up a little bit bigger that way. Yeah.
Is this better?
Works. No, the last one was good.
Okay.
Okay.
So I'm going to assume that this is a flush-mounted array. And the surface behind the PV modules has not been prepared. Like, if you paint the roof blinding white and you have the PV modules mounted a foot off the roof, then you can potentially have some gain, in which case you can add the gain here. But if it's flush mounted, usually there's no added gain there. So I'm going to leave that be.
It's a mono module anyway, so.
Yeah. No, just in the event that it's a bifacial.
I see.
Okay, so we're going to choose Canada. And for series, if you already know what you want, then choose that particular series. Like Primo, Simo, etc. For now, I'm just going to say all inverters. Now, when you are making a choice of the inverter, please make sure that you are aware of as to what the maximum permitted DC voltage on the DC side, the array side, is for this particular design. All right, because if it didn't say /600 volts, it means that's the suggested design for that particular choice of inverter is going to be for 1000 volts DC. Okay, and so if you don't keep that in mind and you get the full thing strung up, then during inspection, if they ask you for this, then you might be in violation of code. So more work, more money, etc., to restring the array. So for now, I'm going to assume that this is going to be a Primo 10 240 for a residential rooftop. So it's going to be 600 volts DC. Now, this is where you also, sorry, I did speak to you earlier about the inverter ratio. You don't really care all that much on the low side. What we are interested in is on the high side. So I'm going to fix that to 150. Oops, sorry. There we go. Now, storage isn't relevant to us here because we don't yet have hybrid inverters on the market here in Canada. So I'm going to leave that be. Now, the way you interpret the design here is once you plug all of those numbers in there and make sure that the numbers are correct, the table underneath here will update itself to reflect suggested designs, possible suggested designs for whatever numbers you plug in. All right. So if you plug in incorrect numbers there, what suggested designs you get from here will be wrong. Okay. Wrong need not necessarily mean it won't work. You might be stringing for 1,000 volts on a residential rooftop if you didn't make pay attention to what.
I think I accidentally muted Harsha. If you want to unmute yourself. Sorry, guys.
Oh, sorry.
There you go.
Wait.
Sorry, my mistake. I accidentally muted you.
Okay. Never mind. That's all right. I hope that wasn't for too long, though.
No, but 20 seconds.
Okay, perfect. Okay, so once you plug your numbers in there, you get to see the table here. And the way you read the table is the first row on the table. You've got numbers in bold on the top left corner of each cell. That is a number of PV modules of the type that you made a choice of, all right? And what's on this table isn't all of the designs you get to see. So if you click on the to the right button, you get to see that the table is quite some, on the right side as well. So let's say I choose the maximum size, which is 148%, because PV modules are modular. And so because you can't have 27.5 or 27.2 PV modules, you have to go with whole numbers. So that works out to be an inverter ratio of 148%, which is 14.85 kilowatts on a 10 kilowatt inverter, okay? Now, the way you read the table is you can connect 27 PV modules in different ways to get you string designs to connect to that inverter. And given that this is a 2 MPPT inverter and 27 doesn't exactly divide equally across the board, you will see that you will have different string lengths, potentially different string lengths, all right? And if you do still remember, I told you always choose to go with the longest of strings because longer strings implies higher voltage implies lesser current implies more efficient system. All right, so always design such that you have less current and more voltage because power is a product of both current and voltage, and less current you have, the less copper losses you've got or less heating losses, I²R losses you've got, right? So I can have 27 PV modules configured as 3 strings of 9 PV modules each. And if I see this option which says PV1 plus PV2, it means you can have 3 strings combined and bought into the inverter and operate the inverter as a single MPPT inverter. That's what this means when it says PV1 plus PV2, all right? And you see this little symbol here, that implies you're paralleling the strings. And if you still remember, we spoke about paralleling strings. You can parallel strings in the inverter or before the inverter. If you parallel them before the inverter, make sure that the cable that you bring into the inverter is landed using a bus bar attachment. So that way you are not overpowering the single screw terminal rated to handle 15 amperes with potentially 45 amperes worth of short circuit current on it. Right, and not to say that it'll blow the device at the outset. We've had so many people do this, especially in Manitoba, because of that particular code requirement, where they work the inverter with 6 strings landed on a single screw terminal rated to handle 15 amperes. So they were landing, potentially 12, 6, or 72 amperes on that single screw terminal. The inverter worked just fine for 3 or 4 years before it fried the terminal. So don't do that. And also they'll come back and say, well, how did it work for 3 years? I mean, you should be lucky that it worked for 3 years because it was rated to handle 15 amperes. You're landing potentially 60 or 70 amperes on it, right? So let's not do that. Again, always, if you have any doubts, ask rather than assume. So in this particular suggestion, you can have 3 strings in parallel with the inverter set up as a single MPPT inverter. If I move my mouse over the tile, it'll change color. Click on it. It'll give you the little pop-up. Do you see the pop-up here?
Yes.
Okay, so now you see here that the MPP voltage at 70C is 323 volts. All right, the open circuit voltage at the lowest site temperature that I plugged in there, which was -40, is 526.86 volts. All right, if it went below minus 40, this is going to rise even higher. So that is the reason I said always make sure that the numbers you plug in there are the numbers you expect to see over the course of the, over the lifetime of that system, and the lifetime of the system is typically assumed to be 20 years. So what is the risk that you will fall, lower than minus 40 C in terms of temperature over that course, that expected lifetime? And so not to say that, remember, this is a primer. The primer is rated to work all the way up to 1,000 volts. So you won't destroy the device, but you can have other components in the system in series which might not be rated to handle 1,000 volts. For example, this is a residential rooftop. Residential rooftops need a rapid shutdown. The rapid shutdown box is only rated for 600 volts DC. Okay, so you might not have blown the inverter, but you might have blown some other component in the system. So that is the reason I said always look at the weakest link. The weakest link is the component with the lowest voltage rating in the series of whatever components you've got on the DC side. That component decides the system voltage. So when I make these designs, you have to keep in mind that every piece of equipment on the DC side is rated to handle whatever potential voltage that array is expected to throw out for the lowest temperature expected over the course of that duration, which is 10 or 20 years, as the case may be. Okay, and they'll also give you your short circuit current at 25 amperes, and you can see that the short circuit current is almost 42 amperes. All right, so again, it's 3 strings of 9 PV modules in series each, all paralleled, because we chose the single MPPT option, and because you are more than 2 strings in parallel on the same MPPT now, it says string fuse is required. Yes. Okay, now we're talking about string fuse is required. Always keep in mind that fusing is a series protection component, which means your point of paralleling, or the place where I parallel my 3 strings, the fusing has to be before the point of paralleling, not after, because any fusing that I put after is redundant, because the short circuit current, the 3 strings where they get paralleled, the short circuit current is in circulation at that point, because that's where you parallel them. So which means the string which I'm trying to protect needs to have the fuse in series with that string before the point of paralleling, not after. So if you do need to have a combiner box, your fusing has to be in the combiner box before the combining, not after, because we have seen situations where people put the fuses, but they put them in the inverter, but I'm getting all of the fuses combined in a combiner box prior to the cable coming into the inverter. So on paper, have you fused? Yes. But is it actually doing anything for you? No. So this is the reason why I said that the crew building it needs to be on the same page as the person designing it. If not, you are working at cross purposes. Now, should you need a PDF copy of this report, you can click on the Create Report button here. It'll give you a PDF copy of this report. So that way you can use that for your records. Okay, now let's assume that I did not want to do 3 strings in parallel and combine them with a combiner box before getting it into the inverter. I can still have 3 strings, but 2 on MPP tracker 1 and 1 on MPP tracker 2. All right, in which case, if I were to click on that here, you will see string fuses required. No, because it's only 2 strings in parallel on MPP tracker 1, which is, you're not going over 2 strings in parallel. And on MPP tracker 2, you've only got 1 string coming in. So if you remember the voltages and the short circuit currents, all of those stay the same between the previous design and this one. But because we are operating the inverter now as a 2 MPPT inverter and not a single MPPT inverter, you are no longer required to fuse. And even if you did put fuses there, your fusing is actually redundant. You're not really protecting anything.
So Harsha, does that mean that with this panel specifically, you cannot do 10 panels in a string in this environment? Is that why that's not given as an option?
Correct, because your minimum temperature decides that.
Yeah,
like
so
I'll give you an
over
example.
600 at that point, right?
Exactly. So if let's go in here. I'm going to change that number here to minus 20, and you'll see that you can go longer in terms of string length.
Yeah, there's a.
You see this? You
yeah,
see
there's
2 times 10.
options.
Yeah.
Yeah. Okay, cool. Yeah, it's good to know as well. As the panels are changing, the number of panels in a string changes. So for example, when I started in the solar industry back in 2012, 2013, panels we used were like 225-watt panels, and I remember doing 13 panels in a string at 600 volts. So obviously, as panels have grown both in size and wattage and voltage, that is a big change. So we're down to 9, and then also the minimum number, I guess, changes as well. So I guess will be fewer as well with the minimum number in a string will be fewer now, right? So what are we at? What is the minimum we see? 4 panels? 3 panels?
You can have 6 panels. You can even have 5 here, 4 even. Okay,
Yeah.
but remember, you got to
There's
keep
3
in
even,
mind.
so
Yeah, but
obviously
this
the
is from a,
efficiency changes, right?
exactly.
Yeah.
Okay, because this is still safe for the inverter. That didn't mean this is the best design you should be going with. So that is the
Yeah.
reason I said that you can run your simulation with helioscope or something else. Okay, but the way you string it up together needs to be checked with the inverter manufacturer's tool as well to make sure it is safe. Just because it is safe didn't mean that's the best design.
Yeah, but sometimes you have 3 panels going in one direction and 2 strings of 10 panels going in another direction. That still means that you can install those 3 panels separately onto MPPT2, right?
Exactly. Yeah.
That makes sense.
Yeah, but it's, typically what I would do is I would always try to dissuade the person from using a string with just 3 PV modules in series, unless of course there's some very strange constraint on the site or the roof space. By and large, I would never suggest any strings with very low PV, what should I say, numbers of PV modules in series.
Sure.
For example, let's click on this here. Now here, you can look at on string 1, everything looks nice and dandy, but on string 2, you can see that the MPP voltage at 70C is literally just, the inverter's wake up
Sure.
voltage, okay?
Yeah.
Yeah, so it's really not, optimal to go with such short strings.
Sure.
Okay, and on the flip side, let's say I'm going to change this up to minus 45, and you'll see that you likely will not even go up to 9 PV modules in series. Oh, you still can go up to 9. Let's say 50 then. Okay, looks like you can go up to minus 50 with mine, with the 9 PV modules in series.
Yeah, I think 9 is fairly conservative still.
Yeah, but always, so remember, this is just a tool, and anytime you use any sort of software tool, I don't know if you remember or if you've heard of this phrase, GIGO.
Never heard
Has
of
anybody
it.
heard of GIGO? So GIGO, which is basically garbage in, garbage out. So which means if the numbers you plug in here aren't real, or basically garbage, the suggestions we get from the tool are also going to be unreal.
Sure.
Now this is more about the product and the installation side of it. Okay, so the products are rated, for, NEMA 4X. NEMA 4X means it's rainproof or splashing waterproof. That did not mean it's water. What should I say? You can't submerge the device in water and have it work. So it's not IP67. All right. So NEMA 4X again is rainproof or splashing waterproof, and the devices are good up to minus 40, which basically means that once you go lower than minus 40, the device will shut itself off. It's a safety feature built into it. Okay. So there's no risk as such, but that also means you should not be working on the device at minus 40. So there is a difference between saying the device is rated to work at minus 40. That didn't mean you should be opening the device or working on it when it's minus 40. Okay. Now, when it comes to the installation itself, remember the inverter is, when it's manufactured, it's NEMA 4X, but obviously to install it, you have to take it apart. So when you take it apart, the NEMA 4X condition doesn't apply anymore because you've breached that condition, right? And so you can see in the picture on the right side that the gentleman has taken the part of the inverter, which we call the power stage, off of the back. The back is the mounting bracket. So the back is the mounting bracket, which is static, stationary, and passive. There is no electronics on it, but that is a place where you what should I say? You fix the mounting bracket to whatever surface or racking you're going to have the inverter attached to, and you're going to get the cabling into the inverter as well. Okay, so when you are doing this, obviously the NEMA 4X condition does not apply. But after you finish your installation, it is a responsibility of the technician to return the inverter back to the NEMA 4X condition. Because if you don't, then basically all of those claims in terms of it being NEMA 4X and splash waterproof, etc., will not apply. Okay. Now, also when it comes to the actual installation process itself, as in like physically putting things together, you always have to make sure that you are paying attention to the torque. All right. Do keep in mind that the inverter body is plastic. All right, and plastic is very, what should I say, unforgiving when it comes to torque. So because the plastic is not self-healing. If you've damaged it once, it's damaged. and there's no recovery for that. All right. And more often than not, what we get to see is people are not aware, or they're trying to save time. And so what they do is they use power tools or drills, etc. Do keep in mind that the starting torque, even on the cheapest power tool in the market, is easily over 5 Newton meters, and the maximum permitted torque on any of these screws is 2.5 Newton meters. So merely starting the screw with your power tool might have actually damaged the device already. And given that a lot of the inverters do tend to get installed outdoors, once you have a crack, come winter, the crack will grow. Okay, and remember, this is to last you at least 20 winters, so you can imagine how much damage you could cause just because somebody didn't pay attention to the installation manual. All right, so that's the reason you will see it's all inverters, the packaging, etc., will literally be plastered with information or little diagrams saying no power tools, because we've seen this happen one too many times. And so you have to remember, more is not necessarily better. It'll work against you. So again, please make sure no power tools ever. Okay, and that didn't mean that because depending on the person or how strong the person is, they could literally over torque things by just using hand tools as well. So if you don't have a feel for what it feels like, pay attention when you're disassembling it with your hand tool, and you'll get a feel for what 2.5 Newton meters is, because all of these, when they do get put together, there are calibrated tools. So when they do get put together, there are what should I say, mechanized tools with torques set on them. So when you are undoing the screw to put things together or assemble things, you will get a feel for that 2.5 Newton meters. All right. Now, this isn't to say that you should be doing that. I mean, if you have a good feel for torque, sure, go ahead. Ideally, what you want to do is use what we call a torque screwdriver or torque driver. Okay. You see an example here. So this is from Wiha. There is another one which is called Vera. I think both of them are German brands. I've not seen very many torque drivers made in North America. So here, if you do decide to go that route, you can see that you've got that little window there where you can see what the torque setting is. So you have to make sure that you set the torque driver to that particular torque set, and then you can use it to tighten, because if you were to go over that torque, the driver will click. So you're not over torquing the screw.
Yep.
Okay, so again, about torque, excessive tightening, you can cross thread or damage the threads of the inverter. And also with power tools, it's very easy to have a misaligned screw completely mash the threads. Okay, please make sure that you don't do that. Always go easy. And if you face resistance, back off and make sure that the screw is you got the thread set right before you force it in. All right. And if you've installed a few of these, you would have known that the cabling and the point of entry for the cable is on the mounting bracket. So the wires, you land them on the screw terminal block. And then, the actual guts of the inverter is the power stage. That is where all of the electronics is, all right? And the power transfers from the screw terminal block, which we call the Benedict block, into the power stage through knife edge contacts. So if you've paid attention to the block, I'll show you the block a little further down. You've got the AC blades on the right side. So there's a row of 6 or 5 slots, depending on whether it's a single phase or a 3-phase inverter. And within each of those slots, there is a metal blade, all right? And that is on the right side for the AC connections. And on the left side, you will see 5 slots again, but these would be in 2 columns, 1 column with 3 and 1 column with 2. And within each of those slots, again, you will have blades. These are the DC blades. Now, that's where the power coming from the array gets to. And if you lay the inverter face down and looked or paid attention to it, you will see that corresponding to those slots on that block, you will have protrusions. And within each protrusion, there is, what should I say, a copper leaf spring on either side. So when I insert or hang the inverter on the mounting bracket and gently ease it into the, the screw terminal block there, those protrusions insert themselves into the slots, and the blades in each of those slots insert themselves between the copper leaves. So it's a sliding contact, and the power transfer happens there. Now, supposing you over-torqued or under-torqued, then that contact is not going to be good. And if that contact is not good, you could have nuisance tripping, because if let's assume that you've got too big a gap there because maybe you have an oversized fitting or something's getting pinched between the power stage and the mounting bracket, you will have poor contact there. If I have poor contact there, you could create what we call a high resistance contact. If it's a high resistance contact, you will start heating that contact. Now, if you heat the contact, because the resistance is going up, you are compromising how much power you can draw from the array. Okay, and in the worst case, if it gets hot enough, you might actually end up welding the copper leaves to that blade. So always, if you face resistance, back off and see, because really when you assemble it and put it together right, you should not face any resistance. If you are facing resistance, there's something that isn't assembling or sitting together right, all right? So again, all of this is not, what should I say, you install and forget. Sure, that's the intention, okay? But if you pay attention to how you're putting things together, you could literally just install it and forget it, all right? If you don't, then you might have to keep opening the inverter and do additional service, unrequired downtime, etc., all that stuff. So do your homework, do your due diligence before rather than after. So fixing problems are easier before than after. Again, if you have doubts, ask, don't assume. Okay. Now, a lot of these torque numbers are in foot-pounds because I've actually borrowed a lot of information from Fronius USA, and they tend to be, what should I say? But they tend to use those metrics, which we don't follow here. So I don't personally have a feel for foot-pounds or numbers in that system. So if you aren't aware, always make sure that you try, convert those numbers to our metrics, which are Newton meters. Okay. Now, in terms of the actual installation itself, so you remember these inverters could be mounted indoors, outdoors, etc. And a very important part of all of this is like like I've had lots of conversations with lots of electricians, etc. And most people who are trained to be electricians would be working, unless they're exclusively working on outdoor stuff, their experience tends to be more for stuff that is installed indoors. Okay. So what that does is it kind of makes you blind to things you might not have expected when you start installing stuff outdoors. For example, we spoke about NEMA 4X, but NEMA 4X is only the inverter, and the inverter is only NEMA 4X if you actually follow through with the standard installation procedures or suggested best practices. So if I'm using conduit, for example, and I have the inverter mounted, so there's several things you can do to make sure that there's less, what should I say, trouble or maintenance required in the long run. So all of this has to be done at the outset rather than after. And if you've installed a few and you're paying attention to the way you install them, this kind of becomes second nature to you, right? For example, if I'm mounting an inverter outdoors and I need to mount it without protection, I'll always choose to make sure that the face of the inverter is facing north rather than south, because we are in the northern hemisphere and the inverter is just electronics. It's literally your computer. So if I'm going to have the computer, you can imagine how hot your laptop gets if you've been working on a laptop for a few hours. It's the same logic as for the inverter. Your laptop has a fan, the inverter has a fan too. So the cooler I keep the device, the more efficient the device is and the less trouble you'll have from the device. So if I'm going to mount the inverter, I'll always choose to make sure the inverter is kept out of the sunlight. If that's not an option, have it face north and things like that. Also, by and large, I would always suggest have the inverter mounted upright rather than horizontal, because usually if it's horizontal, there's a good chance that if you do not use a shade cover, your inverter is going to be buried under 2 feet of snow. And your PV modules, we just spoke about that earlier. So even if I've got like a foot of snow on an array, if it's clean, fresh snow, light is still getting through. So which means that the PV array, once it gets light, it's going to start circulating current. Once you get current circulating, the PV modules will shed snow. So now the PV modules have shed snow, but your inverter is still buried under 2 feet of snow. Okay. Now the inverter does run hot because all electronics run hot. They make you heat, but that heat might not be enough to melt the 2 feet of snow you've got the inverter buried under. So which means you could potentially be having the inverter sitting in a little pool of water, because the inverters melted the water in the immediate vicinity of it, but that pool isn't what should I say, hot enough, if you will, the melt water, for it to get all of the snow off. So what that means is now I could potentially have a situation where I'm literally having the inverter working in a puddle of water. Okay, which is not the best of situations to have the inverter work in. This isn't to say that it's going to fail right away, okay, because that, whether it does or doesn't fail, is now going to be a function of how well the inverter's points of entry for the cabling on the mounting bracket are sealed. Okay, so that's why we have this thing about rain-tight conduit and compression fittings. Oh, sorry, I thought I had that slide there, but give me a second. Okay, so now if I did use conduits and etc., when I get that conduit into the mounting bracket of the inverter, that mounting bracket now, if I do not seal the conduit from the inside, is actually open. So I'll have like a through channel from the other end of the conduit, whichever place that might be. It could be on the roof or somewhere else. And then if I don't seal that conduit, I have an open channel between that, the connection compartment area where you get the wires there and the outside atmosphere. And you have to remember that electrical equipment, the standard operating temperature is assumed to be 75C. That is also true for the inverter itself. So which means the inside of the inverter can touch 75C. And once the insides of the inverter touch 75C potentially, the air on the inside is going to expand. And obviously, if I've got an open conduit, that expanded air is going to force itself out and come out through the the unsealed conduit. Now, the air going out is not the problem, but in the evening, let's assume that this is a peak winter, but it's a cool, clear, cold and clear day, which means it could be -40 outside, but your inverter could be running full tilt, which means that on the inside, it could be at plus 75C, which means now I have a temperature gradient of 75 plus 40 between the external and the internal environments. So the air is going to expand, it's going to force itself out, that's not a problem, but come evening, everything's going to cool off rapidly, which means now the air on the inside is going to contract. If that creates a vacuum, and if you have an unsealed conduit, I'm going to suck cold, moist air into the inverter, and cold, moist air will start condensing on the parts that cool off fast, which is typically the metal components, and which means that all metal components on the inside of the inverter, which could potentially be live, will have condensation on them. And high voltage, 1000 volts DC and condensation is a terrible combination. Okay, so when you do install the inverter, the points of entry and exit for the cabling on the mounting bracket will need to be sealed from within that mounting bracket with duct seal, silicone sealant, or electrician's putty. Please make sure that that compound is rated for that site. Okay, because on the inside that compound could be at plus 75C, and on the outside that compound could be seeing -40. So which means that compound has a temperature gradient of 100 plus degrees across it. And if I run that cycle across that through 3 months of winter, that compound will start crumbling. So always make sure that whatever you use is actually rated for that particular temperature gradient that you expect to see at the site. Okay, so again, we are coming back to this part where we are harping about the pneumophorics condition and the importance of torque. So when you're hanging the inverter up and I'm swinging the inverter or the power stage into the mounting bracket, I should face no resistance. If I do, step back and find out why, because you do not want to force anything. Okay, because there really is no reason why you should not be able to have like a smooth assembly when I hang the inverter up. And I'm then going to tighten the screws holding the power stage to the mounting bracket. Please make sure that you do not over torque those screws, and neither should you under torque them. Excuse me. Now coming to the product installation itself, always make sure that you have information about the site and the expected conditions at the site when you do choose to site the inverter in a particular position, all right? So always, make sure that by and large, you want to make sure that the inverter is kept as cool as possible. So if you do need to have it out in the sun, either choose to keep the electronics, the power stage of the inverter facing north, so that way you're out of the sun. If that is unavoidable, or preferably use a shade cover. The shade cover will not only keep the device cool in summer, it'll also make sure that your device isn't choked and sitting in a puddle of meltwater in winter as well. All right, that's one part. The second thing is, we don't see this often in Canada, but the altitude at which the inverter is going to be installed decides what the capacity of the inverter is. Okay, the reason being, the higher up you go, the thinner the air is. The thinner the air is, the less efficient the air is at cooling the device. So which means if I have a SIMO 24 and I'm installing it at a height of 2,500 meters above sea level, that device will now not be able to function as a SIMO 24, in the sense it will not be able to give you 24 kilowatts. And also keep in mind that the maximum DC voltage that a device operates at is actually a function of that too. Because the higher up you go, the thinner the air. The thinner the air, the breakdown voltage of the air is lower. Okay, so what I mean by breakdown voltage of air means is if I've got a 1 millimeter gap at sea level and under regular standard temperature and pressure conditions, which is 25C, you can apply 3.3 kilovolts before that air starts conducting, which means we talk about air being an insulator, but even that is actually not true. It's a function of the voltage. Okay, so the higher the voltage, even an insulator will start becoming a conductor. So by the same logic, the higher up you go above sea level, the lower the voltage at which the air breaks down, which means you will have to design the strings keeping that in mind. So we don't get to see that often, but if you are in those situations, you always want to keep that in mind. Okay, and the other thing is, you always want to make sure that you do not install the inverter in places where you have people living. So what that means is, do not install the inverter in your living room. Do not have the inverter installed around animals. Okay, the reason being, the inverter makes noise, electrical noise, And it does also make audible noise, but the audible noise or the range of frequencies that we can hear and other animals can hear are grossly different. It's kind of like a dog whistle. So we can't hear the dog whistle, but the dogs can hear it. So it's a higher frequency. So the same way the inverter makes electrical noise and audible noise, but the audible noise could be in ranges beyond what we can perceive, because there have been instances where they were installed on the side of a barn and it drove, the farm animals nuts. So this was an example in the US where the horse kicked the inverter clean off the wall. Okay, so don't do that. And also, if you need to have them installed around animals, please make sure that you do not get the inverter exposed to ammonia, because we've had situations where people install the inverters inside hog barns or hog farms, and they generate a ton of ammonia, and the ammonia will actually start eating through the plastic, etc. Okay, so you'll start seeing white or clear plastic start going yellow, and it'll start becoming opaque. So you should never have electronics installed around very, what should I say, polluted environments, like where you have a lot of ammonia. And if you have a lot of dust, please make sure that you do not install the inverter near dust, because dust is an arc flash hazard, okay? Because dust is explosive and it's also combustible. And if you are mounting the inverter outdoors, please make sure that you have the inverter mounted clear of vegetation, because we've also seen instances where, the grass was growing so tall that it was actually choking the intake vents of the inverter, and the inverter wasn't able to cool itself. So the inverter started derating due to high temperature, not because the temperature was high, because they had vegetation getting through and choking the fans. Now, in terms of the installation itself, you can have the inverter mounted upright vertically and at all angles from vertical to horizontal with the back down, not the face down. Never have the inverter go beyond 90 degrees, as in face down, that side of it, because you will compromise the cooling of the inverter. And do not mount the inverters at angles apart from 90 degrees looking up front, sideways that is, because again, you will compromise the cooling on the inverter. And when it comes to having the inverter mounted, like in a row, one beside the other, please, this, picture here says 4 inches, but I always suggest having 8 inches between inverters, because it's not going to affect how the inverter behaves. But in terms of maintenance, etc., if you need to do something on a mounting bracket, you will not have enough room to maneuver your tools, in which case you might have to take off the inverter and the mounting bracket adjacent to it when you need to work on this one. Okay, so all of this is more in term, keeping in term the long-term idea, in the sense that, remember, the installation is only one part of it. Your system is going to sit there and work for you for the next 10 or 20 years. And in those 10 or 20 years, what's the chance that you might need to work on the inverter and not have enough room, because your adjacent inverter is mounted too close. So although this, infographic says 4 inches, I always suggest 8 inches. Now, a lot of the times, if you have inverters mounted in 2 rows, I always say stagger the inverter installation, because the inverter is a forced cool device, which means there are fans on the sides of the inverter and the exhaust is on the top. So if you look at an inverter installation top down, you can literally see the heatsink on the top. There's a little plastic grate, and under the plastic grate, you've got the heatsink. So the intake is on either side, depending on whether it's a primo or a simo. For simos, it's only on the right side. For small primos, it's both sides, the left and the right. But irrespective of whether it's a primo or a simo or the capacity, the exhaust is always on the top. So if I've got the inverters mounted in 2 rows and you have not staggered them, it's very likely that the inverter underneath the inverter, I've got 2 inverters, so the inverter lower on the lower row is potentially heating the inverter above it. Okay, so which is why if you're going to have them in 2 rows, stagger them. Now, this is about the actual installation, as in like the physical installation of the mounting bracket itself. Now, excuse me, the back of the inverter is flat, okay? But the places where you actually thread your fasteners through that flat portion should only be through the lashes. The lashes are, the word lashes is used for the little cutouts you see on the mounting brackets. You've got these rectangular cutouts. They look like flaps, and also they've got a little play on them. And at the top end of each of those flaps, you've got another rectangular cutout. Your fastener should be threaded through that hole only, that hole alone. Not through the oblong holes. Do not drill holes because if they did make a mistake while choosing the racking, and the spacing on the racking is not going to be lining up with these holes, do not drill through the flat portion, please, because what that does is when you drill through the flat portion and you tighten down those fasteners, you are going to warp the mounting bracket. As opposed to if I did use the holes through the lashes have play on them. So that way, whatever unevenness you might have on the surface behind the inverter, that unevenness is taken up by the play on those lashes. But if you drill through the flat portion, that unevenness is going to be directly transferred to the flat portion. What that does is it'll warp the mounting bracket. And if the mounting bracket does get warped, nothing might happen. Or in the worst case, you might not have the inverter seal and could let water through. Okay, so please do not ever drill through the flat portion to use that hole as a point of fixing. All right, never do that, please. That's one thing. The second thing is, when you do use a washer, please make sure that the washer is only wide enough to sit on the lash, not on the flat portion, because you might have a washer, oversized washer, and it's got plenty of overlap on the flat portion. And now if I tighten on that fastener, I'm doing the same thing as drilling through the flat portion, because you've got so much overlap between the washer and the flat portion. Okay, so always keep that in mind, and make sure that, because I've seen this happen where they didn't pay attention to the spacing on these holes here, and so they drilled through the flat portion and they had the bolt head pushing up against the fan. You've got to remember that the top portion of that mounting bracket isn't exactly empty, because the heatsink of the inverter actually sits in that place. So if I've got any bolt heads protruding there, they could potentially be pushing up against the fan or the heatsink. And if you push up against the fan, you're going to choke the inverter. It can't cool itself. If it pushes up against the heatsink, you're basically getting a bad seal between the back of the inverter and the mounting bracket. So you could let water in there. Now this is about using fittings. When you get your conduits or whatever other sort of cable entry you've got into the inverter. Now you can see that this is showing you a picture from the left-hand side of the mounting bracket with the inverter on the front, right? Now you see that they've got that little yellow ring there. Now the size of whatever you can use on any of these knockouts should not go over 1¼ inches, because if you go over that, then the fixed, whatever fitting you use on the inside to hold that conduit, etc., to the mounting bracket could potentially prevent the front of the inverter from sitting right on the back, because it's pushing up against the power stage. Okay, so you can look at the window here, and that window that you see here is literally the limit to whatever you can have on the inside of it, because if you go beyond that, you could potentially have a bad seal between the power stack and the mounting bracket. Okay, so those arrows show you the window that I was referring to. So it's the light gray window with those circular concentric marks showing you where you can have the knockouts. Now, this is about cable management within the mounting bracket itself. So here you can see that they have the cable entry coming in from the left-hand side again, and they have a conduit, because you see that there is some sort of annular space between the wires and the inside of that conduit. So it's actually open, okay? Now, there is limited room in that little compartment, the wiring area there. And so cable management in this area is extremely important, because if you don't have proper cable management, you could have nuisance tripping because something's getting pinched, or you could have the inverter not close properly, in which you'll damage the inverter as well. Right? So the same logic like before, there are strict torque limits to the screws that you have on these screws as well. So these are the the screw terminations we were talking about, where you land your cables coming in from the array. So the same logic here. So those screws have torque limits on them. We do source these blocks from 2 different suppliers, and they have different torques on them, but the torques are clearly marked on the block itself. So please pay attention to that. So because some of them might have something as low as 1.8 Newton meters, some other manufacturer might have 3.1. So you want to make sure that just like how we said, over torquing is not good, neither is under torquing. And if you have more than one cable more than one cable combined external to the inverter and bringing that combined cable in, then you will need to use the bus bar attachment. The bus bar attachment is shown a few slides further down. Okay, so here you see the bus bar is in use here. So, and the 2 bus bars are mirror images of each other. So please make sure that you always choose to purchase bus bars with both part numbers, because like I said, they aren't identical. They're mirror images of each other. And here you can see that the cable management, it looks neat, but is actually not optimal. Okay, so the problem that you can see that is outlined here is the green ground conductor. So that ground conductor is actually sitting on the switch shaft. So you see that switch shaft, that is actually for the knob on the outside, which is your DC disconnect switch, all right? Excuse me, sorry. Right now, that DC disconnect switch is in the on position, which itself is a problem, because there is a safety interlock on the back of the inverter, and that interlock is going to provide you a little bit of resistance if I'm trying to disengage the inverter from the mounting bracket with the switch in the on position, because if I do that, I could create an arc, because you're breaking a live current when you're doing that. And if you break a live current, you could create an arc, and an arc could be as benign as to do nothing, or it could be as bad as to create an arc flash. So please make sure that your system is de-energized on both sides, AC and DC, before you decide to, take things apart. Now here you can see that he's got the DC ground wire running in front of the switch shaft. And if you do that, when I hang the inverter on the mounting bracket, you will get that wire pinched, and you could potentially prevent the inverter from sitting flush. When I say sitting flush, not to say that it isn't sitting flush from the outside, because on the outside it's just a rigid plastic housing. You will see that, but on the inside you might have pushed up against a printed circuit board, and you should never stress a printed circuit board when being operated at 1000 volts DC. So now here you can see that they've run the wires behind the DC switch shaft. So there's nothing sitting in front of it. So that way there is less risk for anything getting pinched. Okay, so always make sure that cable management in that compartment is clean and nothing is going to get pinched. And also please make sure that here you can see that they've got some sort of a collar with a ground lug on it. All right, so the ground lug should not face up, because if, again, the same logic holds, if the ground lug is facing up, it could potentially prevent the inverter from sitting properly or sitting flush on the back. And again, if that happens, it could do nothing. At worst, it could create an arc. Okay, so like before, if your ground lugs or bushings aren't handled or positioned properly, the inverter will not close properly. If the inverter did not close properly, you could have production issues. You could have arcing, you could have inverter damage, because it could also let moisture in. So ensure that the ground lug is not facing up as in the direction in which you are swinging the power stack into it. Please make sure it's always turned down. So in this picture, you can see that the ground lug has been turned down, as in it's facing the back of the inverter and not the power stack. Okay, so here you can see the ground lug is sticking up, and we've got the picture from two different positions. So you can see on the right side that the ground lug is sticking up. Now you might ask me that it's not projecting beyond the plane of the inverter. The limit to that plane is actually not the edge there, but it's actually the window or the knockout. So you see on the left side that this is a small primal. So you've got three concentric circular knockouts. So the knockout actually is the black plastic in the middle, not the gray area around it. By and large, try to keep everything on the inside, including fixtures, ground lugs, etc., within that gray ring. Because anything that projects beyond the gray ring in the direction that you're swinging the power stack in is going to push up against the power stack. So you can see that the ground lug here is not projecting beyond that plane of the inverter mounting bracket, but it could still be pushing up against the power stack, because that lug is beyond that gray circle that you see there. In addition, you can see that not just the ground wire, even the PV wire here is sitting in front or over the DC switch shaft. And you can already see that the insulation on the ground wire has been pinched in the picture on the right side. Okay, so here again, this is telling you what they've done is they've turned it sideways, so that way it does not project beyond the gray ring. Now this is about sealing it. So remember, the inverter itself, what should I say, on the insides, you can never have any exchange with the atmosphere on the outside, because you could potentially have condensation. So this is the reason that you want to seal the mounting bracket, or where you get the cable entries into the inverter, from the inside, not the outside. Be generous with whatever compound you choose to use. Pack it between the wires, around the wires, within that annular space for the conduit or whatever other thing that you are using to get the cables into the inverter. And also, your cable entry, for whatever purposes, it could be rapid shutdown signal wires, it could be communication wires, it could be power cables, they can only come through the mounting bracket. Do not drill through the plastic housing. It's not meant to be used that way. There is a little circular knockout that you can use, but that isn't meant for cable entry. That is meant for your Wi-Fi antenna if you do have a data manager card on the inside. You should not be using that knockout to get your communication cables into the inverter. Okay, so moisture management is very, very important, especially given that the system is supposed to be working for you trouble-free for between 10 and 20 years. Now, outside of that, there's other thumb rules you can keep in mind. Always make sure that if I'm going to use the inverter outdoors and have it mounted, by and large, choose to go vertical rather than horizontal. And even if I did make it vertical, your cable entry should always be preferably from underneath rather than from the sides, simply because cables coming in from underneath, you will not, okay, I won't say you won't, there's less risk of moisture tracking up because gravity will prevent that from happening, okay? So if I do that, you can have, you could have a conduit going upstream, from there, but you still want to seal the conduit because you might not have moisture track up, but you can still have condensation, and condensation comes with the air exchange. So when I make that mounting bracket, I want to seal it and make sure that there is little risk for exchange of air from the between the insides and the outsides. Okay. Now, supposing you aren't using conduit but getting cabling directly into the inverter, please make sure that you are a little generous with the amount of cable that you have there. Give it a drip loop, because drip loops will prevent moisture from tracking into the inverter. Okay, and also if you do not have enough slack to make yourself a drip loop, you still want to make sure that your cable isn't so short that the stress of bending is going to be transferred to the inverter mounting bracket. Because you should never stress the housing of the inverter, because if I'm stressing the housing of the inverter, you will not have a good seal. And also keep in mind that bend radiuses for cables are dependent on temperatures. If I install something in the peak of summer and I didn't give it a good enough slack, not enough slack on the cable, come winter, the cable is going to be very stiff, which means what was easy and pliable and easy to install in summer is not going to be as pliable in winter. And the stress of that bending is now going to be transferred to the mounting bracket. If I transfer that stress to the mounting bracket, your sealing, even though you might have done a good job of sealing the, the cable entry in summer, that is not going to be as good a seal in winter. And once you break that seal, even if it was pliable again in summer, the seal isn't there anymore. Okay, so all of these, they look like no-brainers, but it's so easy to slip up on these things. Okay, so now this is a picture of the DATCOM cover itself. So the DATCOM cover is the little gray canoe-shaped piece of plastic that you have to take off if you do need to disassemble the inverter before you start mounting the mounting bracket on it. Okay, you can see that there is a gasket on the inside of the DATCOM cover. So this gasket is what prevents moisture from getting in through that area. Now, depending on the size of the inverter, you can have 2 tabs on either side. You can see there are 2 tabs from inside, just underneath that gasket there, or you can have a 1 tab right in the middle. So when I'm putting this together, please make sure that the top goes first, and then you swing the bottom in. So that way you are making sure that that tab is correctly aligned and positioned. And you'll also see that there is a little overlap between the housing, the metal housing cover on the top, and this plastic cover. So this plastic cover actually kind of slips a few millimeters under that metal housing cover. So that way, you are ensuring that it's kind of like a roofing tile, where the tile above is kind of, you've got a little overlap with the tile below to prevent any sort of moisture from getting in through there, because gravity prevents that from happening. And the 2 holes that you see on either side are for the screws holding it there, holding that DATCOM cover to the inverter frame. Now, depending on the capacity of the inverter, this slide shows you where you have seals or gaskets. Okay, so this picture is an exploded view, and so it's I think SolidWorks rendering for a small Primo. For a small Primo, the housing gasket is a little different. So you can see that if you take the front housing cover off, that's where you will see the gasket on the inside. This is the back of the inverter with the face down, but without any of the other components, just the housing. So, you've got that little slot in the middle. That's where you actually have the heatsink. And the 2 little rectangular, or should I say, wells, if you will, are where the chokes for the inverter are housed on the inside. So there's 1 gasket there. And then you've got the second gasket here on the bottom, which is what seals off the connection area from the external atmosphere. So supposing you did have a wire pinched, then you're obviously, you don't have a good enough seal, and you compromise the integrity of the inverter, which could be one of the reasons why when you're hanging the inverter up, you face some sort of resistance. Which is why I say that when you hang the inverter up, you should not face any resistance when you swing the power stack into the mounting bracket. So this is an actual picture. So you see the gasket here. And remember, we were talking about those protrusions. And given that this inverter is face down, the AC terminals are on the left side because it's like mirrored. Okay, but if it's the right way up, the AC terminals will be on the right side. And you can see that this is a small Primo. So on a small Primo, you only have 3 positions on the DC side. That's why you only see 1 row of 3 terminations on the right side there. So the protrusion on the right side are your DC protrusions, and the ones on the left side here are your AC. But when you hang it up the right way, your AC is actually on the right side and the DC is on the left side. And you also get to see the red arrows here, which are showing you where the gaskets are for the rear of the inverter. So when I hang the inverter up, this gasket is going to make contact with the lip of the lower compartment there, and that's how you get an an airtight and watertight seal. But if you have not sealed the compartment at the places where you get the cable entries in, even though this might be airtight and watertight, you still have an through channel between the insides and the outside because that conduit isn't sealed. Okay, so here you see the right way to put on the DATCOM cover, and remember we spoke about the overlap. So you can see that the metal housing cover on the top, you've got a little overlap with the plastic cover, the DATCOM cover. So the top goes on first, so that way you're ensuring that the tab on the inside is making good contact and aligned properly, and then you swing the lower part in, and then you'll hear a little snap. Now, supposing you do not install the DATCOM cover properly, you could get moisture coming in. And so obviously if it's not sealed properly, it's not NEMA 4X and you'll have a higher failure rate. And the same thing as before, the screws here, 2.5 Newton meters, don't go over that. Okay, so again, always make sure that the inverter is only installed ever between, looking at it sideways, between 0 degrees, that is flat on its back, horizontal, or true vertical. And everything between 90 degrees and 0, but not beyond. As in, you cannot have the front of the inverter facing, low, like beyond 90 degrees. Okay. Now, anytime you have to work on the inverter or put things together, your DC and your AC should be off. All right, because if you don't, you're breaking a live circuit, and it's a fire hazard if you're trying to break live circuits without powering it down first. When I'm mounting, or you are mounting the mounting bracket onto whatever surface you are mounting it, use a minimum of 4 points of fixation. Okay, 3 are the bare minimum actually, but the 4 is what is recommended. So 3 are to arrest motion in 3 directions because we live in a 3D world, and the 4th one is to ensure that you don't have any play. And you make sure that whatever fasteners you use are only going through the holes that we spoke about earlier. Please do not drill through the flat portion. If you do, depending on the surface behind the inverter through which that fastener is threaded and assembled to, you could warp the mounting bracket. If you warp the mounting bracket, it's not NEMA 4X. If it's not NEMA 4X, you could have moisture entry. Moisture entry will obviously damage the inverter. Only ensure flat washers, okay, because some people tend to use serrated washers. Do not use serrated washers because serrated washers will eat through the powder coat on that. If I eat through the powder coat, although it is aluminum, you typically don't want to eat through the protection that is provided by the powder coating. And also make sure that the washers are not so large that they project beyond the lash and onto the flat portion. If that is the case, then you can slip the washer behind the mounting bracket onto the lash, because I told you earlier, the lash does have some play. So you can still thread it. Just make sure that if you use oversized washer, you assemble it with the washer behind the mounting bracket and on the lash, so that the washer doesn't extend or project onto the flat portion, because you'll defeat the purpose of having the lash there. And then when you mount the inverter is the power stage that we're talking about, or the power stack, onto the mounting bracket of the inverter. Please always make sure that, excuse me. Oops. Okay, it looks like I'm going beyond time. I hope that's okay.
You're okay, okay. Let's just let's just keep moving here, and let's get to the I know you were originally talking a little bit about monitoring, but I think that's something we should be covering in a different meeting. We don't want to go too long because people will lose focus eventually, right? So
okay, so again, all of this is very important because your inverter is only as good as how well protected it is from the elements, and putting things together is what prevents the elements from getting inside the inverter. So again, make sure your DC disconnect, you don't have wires in front of it. You do not have oversized conduit fittings, because if you have anything projecting beyond this, those windows or knockouts, you could prevent the inverter from sitting right. You make sure you do not have ground bushing interfering with the inverter. If you do have wiring external to the inverter, make sure that whatever you have on the outside of it is well protected against the elements as well. In terms of water ingress, make sure your DATCOM covers are assembled properly, and drip loops. You can have weep holes, just not on the inverter. All of this has to be external, and you should not have any sort of moisture ingress anywhere into the light portions, either inside the inverter or external to it. Okay, now in terms of commissioning the inverter, it's not rocket science, it's very simple. The only thing that we request is the person who is commissioning the inverter should be well aware whether they have a single MPPT setup or a multiple MPPT setup, because if they don't, then you might be commissioning the inverter incorrectly. And please always make sure that you know what country setup you're commissioning the inverter for, because if not, the inverter is going to, like, for example, if I chose, you've got a 3-phase 208 connection, but I choose a 240 setup, the inverter is expecting to see a 240 voltage, which it won't, so it'll complain saying there's low AC voltage. That does not mean that you have low AC voltage, it just means that you chose the wrong setup. Okay, and again, we spoke about having the MPPT2 on or off. And yeah, so once you've commissioned the inverter, it'll say wait master ready. And by code, you're supposed to wait 5 minutes before the inverter goes into production, and you'll see the grid test timer. You've got like a scrolling bar. The length of that bar is your countdown timer. So this is again about the same, it's a rehash of what I already spoke about. And this is your connections for the DIN rail. So the DIN rail is provided so if you did need to use auxiliary protection, like surge protection devices, for example. So this is an example of your surge protection. This is about fusing. So integrated fusing is only available for these models of inverters, not for every inverter. Oh, sorry. This is your bus bar. All right, so remember they are mirror images. Now, this is just to show you incorrect spacing between the inverters. This isn't even 4 inches, it's more like 4 millimeters. And this is about hanging the inverter upright. And here you can see that they've used oversized conduit fittings, preventing the inverter from sitting flush. And so they've had an arc. You can see how crisp it is on the right side, AC. Now, this is because they did not seal the inverter properly. They also have a ground bushing sticking up on the right side. And also, it looks like they let water through. So they had a nice arc on the DC side. So again, none of this is to frighten you. This is just to show you, because what we do is we do collect pictures from the field. And now here you can see that they did not install the mounting bracket correctly. So when they torqued it down, the unevenness of the back was transferred to the mounting bracket because they did not use the lashes. And here they basically slammed the inverter down with the DC disconnect in the on position. So the interlock is bent. And here you can see that they've used oversized fittings with the ground lug sticking nice and, it's like a sore thumb. So they had an arc because it didn't sit flush. Now for safety features, the inverters do come with built-in isolation measurement, but the isolation measurement is only active either when the inverter is restarted or when it wakes up in the morning. On the AC side, you have residual current monitoring unit, or CMU for short, anti-islanding, polarity. So if you've got reverse polarity on the DC side, there are semiconductors on the inside of the inverter to tell you that. Overvoltage is not built into the inverter. You would need to use surge protection on it. And the inverter will derate if it's running too hot, either because the fan's choked or there's not adequate ventilation beside it. Okay, so these are the different integrated features that are available with the inverters. If you've set a few of these up, you know what the ins and the outs are. They are for your daisy chaining. And you've got the 3-pin plug for this thing. That's position 5 that you see here, which is normally used for rapid shutdown. And then you've got position 1, which can be used for energy management. And then you've got the digital IOs, which are for the data manager card. And that's your LAN port, should you have wired Ethernet. And there's also a Wi-Fi antenna if you choose to go the wireless route. Okay, now this is for the monitoring side of the business. So for the Snap inverters, you do need a data manager card, and the data manager card is only required on one inverter, and you can have, multiple inverters connected to that one data manager card through the daisy chain. Your daisy chain has to be necessarily shielded Cat5 or Cat6, because if you go unshielded, you will build up static on it. So you will get noise, and noise can tend to corrupt the data coming through. So you will see flat lines instead of getting real data, okay? And one data manager can handle up to 100 inverters, or the sum length of the cabling between the inverters reaches 1 kilometer. Whichever happens first is the limit to the size of the system in terms of the numbers of inverters that data manager can handle. So the data manager is the guy who gathers information, and the data is stored on the data manager card. Okay, so even if I did lose my internet connection, the card itself is holding on to your data. So once you get your internet connection back, it'll go in and backfill all of the data from the days for whatever the time duration that you had lost the internet connection for. But if I have a break in the daisy chain between the inverters themselves, then the data isn't even going to get to the data manager card. So you've got no data to go in and backfill things there. All right. So once you've got the account set up properly and you start receiving data, the data is then stored onto your account on the monitoring platform, which is SolarWeb, which can be accessed either through a browser page, through an app, or through Fronius Solar TV. Okay, so this is just a picture of the data manager card. You see the 4 LEDs. Okay, and you can have the system set up to work with Modbus or other third-party communications as well, but you still need to set it up with the SolarNet loop or the daisy chain between the inverters here. Now, this is just for a demonstration of this thing. I just hope that we still have it. So there is an issue with the site right now, so it's currently being maintained. So that's the reason that it's not just this particular system, it's every system that's offline right now. So this is what your system will look like if you set it up the right way. Now, this particular system has a smart meter, but currently since it's offline, you don't get to see that. This is on the overview tab. So if you log into an account and this is your landing page, what's interesting would be the analysis tab, because here's where you actually get to see the history for your system. So remember, I told you there's a bug. So it told you it was offline, but it's actually still online here. So if you want to see production history, this is where you would go. Choose your devices. You can choose the energy meter here, or you can look at total power or AC voltage here. So you can see you have no data for yesterday, sorry, for today, but yesterday seems to be in a good day. So you can be in the day view. You can see that here. You could be in the month view, or you could go to the year view. This is for the year so far. If you go to the previous year, it'll give you a stacked bar chart. He's got 3 inverters. So each of these colors corresponds to that particular inverter. If you ever want to see what the total system history is, just click on total. It'll tell you how old the system is or when it was installed. And then if you do want to look up your service messages, you can go here. Now, there's a very well installed system. He's got literally no service messages. So they did have a few last year. So you get to see all of those here. Okay. I don't want to take up any more time. We've already gone a little too much. So if you do have any questions, let's have them now. Oh, it looks like the website's back.
There you go. Couldn't wait an extra 2 minutes, right? And then it would have always been up. Then we would have been up. Anyways, yeah. Cool. No, I appreciate it, Harsha. That's very, very insightful. There's lots of information to digest. If anyone have any questions?
Okay, so I'm going to either take that everybody got everything or everybody got nothing.
There's a lot of information there to digest. And what would be the best way for people to get a hold of you if they have any technical questions, Harsha?
See, the best way would always be to write to the PV support queue. Okay. Because if you do write to me directly, and if I'm not in the office, it won't get answered till I'm back. But if you always, even if you did choose to write to me directly, always copy the PV support queue. But by and large, the PV support queue should be the primary point of contact. You could also call in. You can always, leave us voicemails. We typically, if it's within working hours, we will return the voicemail within the hour.
Okay. And what did you say? What was that website? What was that your email that they should write?
That's PV, short for photovoltaic. So that's pv-support-canada@fronius.com. Okay, and you will know you got the right email address because you should receive an automatic bounce back that tells you that the server got it. So it'll be with us shortly. If you didn't, you've got the email address wrong.
Okay, sounds good.
Okay, and go ahead.
And of course, we have lots of in-house help as well. We've got Alexander Wolf, or most of you that have worked with us in the past know him and how knowledgeable he is. So we'll be happy to help out. Generally, those will be more higher level discussions as opposed to specific like nitty-gritty Fronius questions. But when it comes to design and string inverters and all of that good stuff, we have a lot of knowledge in-house. Also, your account managers that you'll be working with, or myself, please feel free to reach out via on LinkedIn. You can send an email to sales@Frankensolar, and I will get that, or Alex will get that as well. So feel free to utilize that as well.
And we do offer trainings on demand. So if you got
Perfect.
crew or you're using Fronius for the first time, you can always write to us and request a training. We'll definitely make that happen. We could also arrange for on-demand webinars. And if you need, you might be traveling to a site which is a few hours away and you're not sure, you might be able to get somebody on the phone to talk to you or help you with. You can always let us know a few days in advance. We'll make you an appointment, so that way we call you instead of you calling us.
Perfect. Well, again, thank you so much, Harsha, and thank you everyone for attending and staying till the end. And we will do a number of webinars here in the next little bit. I think we've got one planned very shortly with about AP Smart Rapid Shutdown, which is a big topic, and some other ones that are going to be coming down the road. I think we've got about 15 or 16 scheduled so far for this year. Only the 2 have been announced, but there's lots to come. So keep an eye on your emails. So we do another email blast, and then also we post all of them on LinkedIn and on our other social media accounts. So you can always check that as well. And join us again. Thank you very much, everyone, and have a good day.
Thank you for having me, and thank you. Bye-bye.